Okay. Welcome, everybody. Hello. This is our second session of the 2022-2023 Forest and Climate Learning Exchange Series. I'm Kylie Clay, your host today and the Associate Director of the Forest, Carbon, and Climate Program at Michigan State. I want to give a quick thanks to our co-host, the Society of American Foresters, or SAF. SAF is the national scientific and educational organization representing forestry and related natural resources professionals across the United States. Founded in 1900, SAF promotes science-based sustainable management and stewardship of the nation's public and private forests. So we're very happy to have them as co-hosts this year. Thank you to our additional sponsors, NCX and Renew West. So today we have Erin Weiskittel and Erin Simons-Legaard from the University of Maine. They'll be presenting Assessing Landscape Scale Climate Smart Forest Management Strategies. Is it possible? So among other things, we'll take a look at their approach to doing so in Maine, and hopefully a takeaway will be that yes, it is possible. Before we get started, just a quickly look at some housekeeping details here. So first, to automatically receive registration details and information regarding upcoming webinars, please do join our mailing list if you haven't already. You can email us at forestc@msu.edu. A recording of this session, along with a copy of the slides, the PowerPoint slides, and will be posted to our website. And alongside, we'll drop a link in the chat here where you can access that, and you'll also see all previous recordings and PowerPoints from previous presentations there. The presentations will be followed by a Q&A. So the last 15 minutes will be a Q&A thereabouts. On the bottom of the Zoom interface, you'll see the word chat. So there you can offer questions at any point during the presentations. We'll kind of behind the scenes be compiling those questions, and then we'll pose them to our speakers during that Q&A, that designated Q&A time permitting. So if you are calling on the phone, and so don't have access to that chat box, but you can email us. You can also email us at forestc@msu.edu, and we will be collecting questions there as well. For continuing education credits, so anybody here, all of our attendees are qualified to receive half of a CFE credit from SAF. This will be automatically communicated to SAF, and you'll receive the credit if you've registered with your information on the SAF account. If you have any questions about this, reach out to us again. Our email is forestc@msu.edu. Attendees are also qualified to receive one CEU credit from ISA in either the management, certified arborist, or municipal specialist category. If you would like to receive ISA credits, please email us. Again, that's forestc@msu.edu within the next 48 hours with your certificate ID number, and we will take care of that. So that's all I have for the background here. Erin and Erin, our two Erins, will you please go ahead and steal the screen away and begin your presentation?
We sure will. Thank you for having us. I'm very excited to have such a large audience. I'm very excited to present some of this work that we've been working on for over a decade now. And I think it's timely and very focused. Definitely a very impressive webinar series. I know many of the speakers, so sounds like it's been a great event and very delighted to be part of it. Even better, there's such a great turnout on, at least here in Maine, a very beautiful late fall day. So really delighted to be here. Erin, I'll start up first. I'll try to set the context for a lot of what Erin has been working on. I did also want to acknowledge many of our partners and longtime collaborators, Adam Dagno, who probably should be giving this talk, but is currently on sabbatical in New Zealand, and a longtime University of Maine faculty member, now working on to phased retirement, Ivan Fernandez. I just want to acknowledge this has work been led and kind of partially funded by the Center for Research on Sustainable Forests, which I oversee. I'll just say quickly that I think these buzzwords, natural climate solutions, climate smart solutions, have kind of been, I would say, academic jargon. There's a lot of recent papers. The USDA just put out a $1 billion RFP around climate smart management. I think a lot of what's motivated our work in Maine is working directly with the landowners here and trying to look at actual feasibility rather than just kind of broad scale calculations and assessments. So this is actually putting research to a practice, which we feel very proud of and have a long history of doing here at University of Maine. I think obviously climate change is a big factor as we think about carbon or climate smart. Maine, as many of you know, are situated kind of in this boundary zone. We're expecting to get slightly warmer, but much wetter, which probably is a boost for potential productivity in the forest. But you can see many of our species are either kind of at their northern or southern limits. And so small changes in environmental conditions can have pretty dramatic effects. Historically, they've always been thought of as kind of the spruce fir forest. What we're seeing now is it's becoming much more mixed wood. So I think the implications for future productivity and composition are unknown at this point. That's been a big focus of our research. But clearly what we see as management, both adaptive management and just general management practices on the landscape are critical for maintaining the forest as productive as it has been. I just want to highlight some recent work that Chris Woodall of the U.S. Forest Service and myself worked out. We were very excited about this analysis because it really emphasizes the vulnerability of our forest. If many of you maybe have taken your forest mensuration classes long ago, you might have heard of a measure called relative density. It's just basically a value that's assessing the carrying capacity of the forest. We looked at this basically over the last 2 decades. Kind of time one on the left here is 1999 to 2012. Time two is the more recent, 2013, 2020. And we leveraged the FIA database. The sweet spot is kind of between 0.3 and 0.5, so that kind of light blue area. And you can see in time one, the majority of the US is in that kind of light blue area. In the last decade, what we've seen is a population or a great increase of the red area. Generally, when we think about relative density, anything above 0.55 is very vulnerable, and likely what you're going to see is increased natural mortality, even beyond just climate change or other kind of natural disturbances. So as we think about carbon, we have to recognize that our forest is at a potentially critical biological tipping point, and that's particularly true in kind of the northern forest or the New England area. As you can see, New York, Vermont, New Hampshire also increased in red a little bit, but by far, 23% of Maine's forests are now outside of that kind of sweet spot of 0.3 to 0.5. So beyond carbon, climate change, or just management itself, I think we have to think about where the forest is in terms of its successional stage and how we want to manage that resource going forward. And this is definitely another complication in that whole mix. One argument as it relates back to the carbon markets, this is recent work that Tony D'Amato, I see that's going to be a future speaker in this series, Chris Woodall and a few of others, as I put up. One of our kind of current issues is the basic baselines that a lot of carbon market programs are using, like BASEWAR or just total carbon, are trying to increase carbon stock. And really what that does is it exacerbates these conditions that we're already seeing on the forest. The forests are already kind of at this vulnerable state. Now, if you're trying to stock more carbon into these, there is a critical tipping point there. And so one of our arguments is using more biologically based measures like relative density that supports forest stands that are not just above stocking, but also below stocking. And that gives you a greater flexibility in the management tools that you need to work with. I would like to think that Maine has been a real leader in terms of climate action plans. Our governor has formed the Maine Climate Council back in early parts of 2020 before the pandemic. And we released this report in December 2020, as well as follow-up reports that really highlighted the importance of putting good science to practice. And that ranged all the way from urban areas, but when you're 90% forested, a big part of that is dealing with the forest. One thing that the center has been a real leader on is in conjunction with that climate action plan. Unfortunately, we have world experts like Dr. Dan Hayes, who has done this at a global scale. We basically did a statewide carbon budget, and this is one of the first that I've seen that include both the greenhouse gas emissions, but also all the sinks and sources of the forest. And we accounted for urban areas, agriculture, coastal and inland waterways. But as this is highlighted here, again, we're 89% forested, primarily privately owned and managed. You can see based over this last decade, about 60% of the state's greenhouse gas emissions have been captured through the forest, just the basic growth and sequestration processes. A portion of that goes into long-lived products like our saw logs and other fiber uses. That's another 15%. So really, overall, the state in Maine is at least 75% of the greenhouse gas emissions are being captured by the forest. Our take is that we can probably increase that amount and offset the entire greenhouse gas emissions for Maine. When you put this all together, only 3% of the other areas of inland water bodies or coastal areas are offsetting that. So really, that's the forest is the focus here. And both our policymakers as well as forest managers feel very empowered by that mindset. We did receive a little bit of criticisms that maybe we're just looking at a small snapshot in time. So this is going back using U.S. Forest Service data back to the early 90s. And you can see that the forest has definitely increased over time, but we've hovered anywhere from about, I would say about 10 to 20% from the actual removals. So it's not a recent phenomena. The bigger question is what happens over the next decade or two as climate change and the impacts that we expect continue to ramp up. In terms of where Maine ranks as a percent greenhouse gas removal by state, actually it's Oregon that's #1, but Maine is definitely in the top 5 with a #4 ranking. So it'd be #1 through some adaptive management practices that are coming forward through the Climate Council. The Center for Research on Sustainable Forests, we really take the land grant mission to the next level by focusing on both research, education, and outreach. As I mentioned, Adam Dagno is a great faculty member here, been here for 6+ years. He came and started the National Climate Solutions Initiative within the center. We're very proud of this work because it's led and relies on strong engagement with stakeholders. And as you may know about Maine's forest landowners, they're highly diverse. They have a long history, and it's not just a planted forest. It's a very mixed and naturally regenerated forest that's very extensive. We recently put out this Natural Climate Solutions Initiative report that both assessed forestry and agriculture. And this is now being kind of implemented in practice. And what Erin will talk about in a second is how do you go from a state level perspective to an actual on the ground implementation and do this in a spatially explicit manner. A lot of what Adam's work has done is we don't want to just look at the biophysical forest itself, although that's a primary driver. We recognize that markets, policy, and other drivers of the forest are part of that. And so as part of this, we've built an integrated biophysical and economic framework that addressed and accounts for many of the things that we're talking about: timber prices, carbon prices, the cost of actual doing management or operations. A lot of what Erin will talk about is the kind of the biophysical modeling. How do trees grow into the future? Which species come after management? What are natural disturbances like spruce budworm or other factors might have on this forest? The key takeaway in this report, you can see the top half is agriculture. So the scales are pretty difficult to compare. Again, when you're 89% forested, if you want to talk about carbon management, then you have to talk about the actual forest itself. And what we try to emphasize is that not one single solution achieves it all. It's about a balance of very active but adaptive management practices. And they can have pretty dramatic effects depending on where you put these management and the intensity of what they want. One of the things that we've been putting forward is an idea that was put forth by Dr. Bob Seymour and Mac Hunter about the triad. And the triad is basically the linkages of different management practices, including intensive management, extensive management, as well as conservation, which ultimately has the most impact. And you can see that in the management practices highlighted in red. Another key factor about that is what's the break-even price in terms of carbon. So many of these management practices are around maybe $20 to $25 per ton of CO2 equivalent, which we feel is very competitive with today's market. So these are both biologically doable as well as economically. I just wanted to finally mention, and I'll turn it over to Erin here in a second. As I've mentioned, our landowners, our commercial landowners are very diverse. They represent a variety of different organizations. And so I wanted to really highlight John Hagan, who is former president of Manomet, a real leader in working directly with landowners. John is retired and living in Maine and really wanted to try to tackle this carbon issue. And so he formed what's called a forest carbon for commercial landowners. So this includes folks like the Nature Conservancy, the Irving, Bascahegan, other primary landowners in Maine. And the question that they set out with is, can northern Maine's commercial forest store more carbon without reducing harvest? The quick answer is yes. It's slightly complicated just because it varies by landowner or what forest type we're looking at. But this report is forthcoming in December 2022. So if you'd like to see some of the details, I would encourage you to stay tuned or reach out to Tom Walker or Adam Dagno from there. From that, I'll turn it over to Erin and let me stop sharing my screen and give her full control as well.
Okay, so I'll pick it up right there. So Maine's forest has been acting as a big carbon sink. And as we look to the future, many are wondering if Maine's forest could do more, could be encouraged through management to increase carbon sequestration or storage. To get at that kind of question, we use computer models that allow us to simulate forest growth and management, ideally over large areas, so we can consider cumulative effects across many owners. The northern half of Maine, this area that is outlined in black, is about 9 million acres. This has been the focus of our research for the last 10 or more years. This area is comprised of unorganized townships. There are many seasonal lakeside camps, but the only permanent settlements are sort of around the edges. The interior is predominantly commercially managed forest owned by a mix of corporations, investment companies, and a few individuals or families. As you can imagine, it has a very long history of logging going back to the 1600s. The first mechanized harvesters showed up in Maine in the mid-1970s, just in time to salvage dead and dying trees from the last outbreak of eastern spruce budworm. Since then, there have been big regulatory changes, lots of ownership change, but always a relatively steady stream of wood coming from this northern area. For the last 20 to 30 years, the annual harvest footprint has been about 500,000 acres a year. So it's a very dynamic landscape, and for that, you need a dynamic model. So in the Landist 2 forest landscape model, the forest is represented by a grid of interconnected cells. Now, how big a cell is depends on the input data. In our case, they're 30 square meter cells, or that's about a quarter of an acre. Each cell has to be populated with information about what species are present, as well as the approximate age of the trees. Multiple species and ages can be present in every cell, and each cohort within a cell competes for growing space under the assumption that only so much biomass can be supported per square meter. Where the information comes from that's used to populate the cells with this information is usually through a combination of remote sensing and ground-based inventory. So here I'm going to pause for just a sec to give a shout out to our colleague, Simons-Legaard. He's the remote sensing and geospatial modeling expert among us. And it's his work on tree species mapping that generates the awesome maps that I then get to use as input into Landis. So U.S. Forest Service FIA plot data also features very heavily in our work, as it serves as our reference data for predicting tree species occurrence and abundance. Here in Maine, there are about 3,500 plots, each of which are measured once every 5 years and have been so since 1999. It's a great data set to work with, and we've had a very good experience working with the U.S. Forest Service to develop research around our shared interests. However, because FIA subplots are not the same size as either a Landsat or a Sentinel satellite image pixel, and there's also locational error associated with trying to line everything up, developing highly accurate maps from these data is not an easy task. And to deal with those inherent data issues, which are in both cases, the scale mismatch between the pixel and the plot side and the location mismatches that can happen, both actually generate the same problem, which is what is termed attenuation bias or systematic bias, so that areas of low abundance are overpredicted and areas of high abundance are actually underpredicted. Everything's sort of predicted to the mean. And we saw this as a problem that needed fixing before we started doing simulations. And so a lot of work has been done to try to increase the accuracy of the maps that we actually use for input into Landis. We've been focusing on species that occur within this northern Maine study area that occur at greater than 10% relative abundance, which includes these 13 species. So we've got conifers on the left and the hardwoods on the right. And when all the hard work is done, we end up with maps of relative abundance per species based off of biomass that we can then use to identify the most abundant species in each cell. But as I said, we also need to assign approximate ages to those species that we're putting in those cells. And further, it's important that we represent the disturbance history that's present in our initial landscape. It's part of what we use to inform not only forest age, but to help guide the program and in the stands that it selects when we do our simulations. So this map here on the left is an ownership map. So you can see where the area that our northern Maine study area encompasses, it has a diversity of ownerships. We've got approximately a little over 500 parcels and 80 owners within that area. It's not uncommon at all for owners to have non-adjacent parcels. So I'm going to show you on the right a time series of forest change going back to 1975. So as each new color comes up, that's the harvest footprint within a 2 to 3 year period. So at the end of that, you can start to see Maine's big state park here, Baxter in the middle, as well as some other areas that are owned and managed by the Nature Conservancy. So over the course of those 35 years, approximately 55% of northern Maine was harvested in some way. And that's a harvest legacy that we want to make sure that is actually represented in our input data and informs things like forest age. So after you combine all of that with a lot of information about species level, a lot of species level information about how individual species grow, as well as mortality patterns, we're able to use the model to estimate live above ground biomass, or here I'm showing you carbon. We validate all of this against U.S. Forest Service FIA plot data to make sure that our initial landscape is as accurate as possible before we use it as the basis for simulation. So for each species, we have these sorts of carbon density maps. So to give you a sense of what Landis looks like in operation, I'll show you a demo for a small area here. So in addition to harvesting, as Erin said, Maine's landscape also experiences wind disturbance, such as blowdown, and so which creates small canopy gaps. So that's also part of the simulations. So you'll see some little blowdown events, as well as some harvesting. The effect is very similar to the satellite-derived imagery, which is by design. We've done a lot of work to try to ensure that the representation of harvesting in Landis, in terms of the shape, size, and intensity of the harvesting, is based to the maximum extent possible on empirical information. So at the end, you can look at your initial landscape and then some later point in time and start to make comparisons, in this case in biomass. So you've got, if you look down at this stand here, you've got some areas that have gotten darker as biomass has increased as a result of growth and aging, but also areas that have gotten lighter as a result of either blowdown or harvesting because trees have been knocked down and there's been a regenerating event effectively. So that's biomass. We could also look at things like all of this has impacts for productivity. So we've had a lot of productivity changes over the course of those 25 years as a result of either forest aging, as well as harvesting that changes the species composition or age of the cells within a stand. Okay, so then we can scale all that up and start making comparisons between scenarios that represent some change in a system driver. So in this simple example here, where I'm showing you total forest carbon on the y-axis and time across the bottom. So this is what would happen if all harvesting were to cease tomorrow. We can get a sense from this of the system capacity and constraints related to forest growth. And although it's a useful point of comparison, it's not a very realistic scenario. The model is not deterministic, like something like FVS. Instead, it does have some stochastic elements. And we've developed methods to actually try to augment that stochasticity or uncertainty so that we're capturing some of the potential effects of year-to-year variation or owner-to-owner variation in harvest rates or patterns. So the gray lines are these different runs, and then the dotted lines are the average values. So instead of asking sort of black and white questions like that, we like to ask interesting questions about how future forest management might change if there were widespread, how future forest conditions might change if there were widespread changes in forest management. We've used Landis to look at a variety of forest-related issues, most recently adaptation to climate change through increased carbon sequestration or storage. And just to give you some examples of ideas that we've been exploring, a common suggestion for increasing carbon is to extend harvest rotation. In our case, in our landscape, in this example that I'll be showing you, I've increased the minimum age requirement for stand selection for harvest from 50 to 100 years. Alternatively, we could consider different silvicultural changes. Currently, about 95% of the harvested wood from northern Maine is removed by some form of partial harvest. This has been the case since the early 90s in the implementation of Maine's Forest Practices Act, which placed some disincentives on clear cutting. The typical partial harvest in this landscape is a combination of overstory removal from the harvester trails and partial canopy removal from the matrix between harvester trails, which in total ends up adding to, on average, about a 50% removal of the stand's biomass. So we've asked, what if instead partial harvest removed less wood in a given entry, but stands were re-entered more frequently, and more of a sort of repeat thin style partial harvest? What if instead partial harvesting or the harvest regime in Maine were to shift towards greater reliance on even aged management strategy? In this example that I'll be giving you, specifically clear cutting. So if we just increase the percentage of removals that are being removed by clear cut. As Erin mentioned, most forest management in Maine depends on natural regeneration. What if instead planting was incentivized, particularly in those clear-cut areas? So if we added planting to the mix. And finally, for something entirely different, what if there was no change in management, but instead what changed was the land base? So between the reserves, the parks and lands, and regulated areas, about 6% of our study area is already excluded from harvest. What if we increased that to 20%, for example? We did this by first identifying all of the shoreland buffers, which there are a lot of. Maine's got a lot of water bodies, where harvesting is already limited by regulation to some degree. And we excluded all of those areas from harvest, which ended up adding up to about 20% of the land base. So those are a list of some of what we've been considering in terms of potential strategies for boosting carbon sequestration or carbon storage. So after multiple runs of each, we can compare average outcomes across the scenarios. So in all cases, we use this kind of extended spin-up period here where all scenarios are treated as the same for the first 10 years, just to kind of get everything going. And then we differentiate between the scenarios and let them run out another 50 years in this case. So the black is our business as usual scenario. So this mimics the recent trends in harvest rates and patterns and stand level removals. We model all owners individually. So we actually use that disturbance time series and pull out individual kind of owner rates and things, and we perpetuate those or mimic those moving forward through time with some stochasticity baked in. And then we've got the biomass outcomes as modeled under a change in management from business as usual to one of these 5 potential adaptation strategies. So each strategy brings with it a different trajectory of total biomass. So we've got some here at the top, like plantations or increased set-asides that immediately pay dividends in terms of total forest carbon. We've got others like the extended rotation down here that start out lower and then catch up and then surpass our business as usual. And then we've got others like our switched even age management that in this case, there's no planting here. We're just switching from partial harvest to clear cutting that remain lower. But although it's appearing like it's maybe going to catch up to our business as usual, but it remains lower for at least the 50 years of this simulation. But this is only one metric upon which to make decisions, and multi-objective management has a big focus of our research. So my focus has always been on multi-objective management, specifically through the lens of wildlife habitat. I'm a wildlife ecologist by training. So I look at how different management strategies not only affect things like carbon, but also ecosystem services, including, in this case, I'm including here wood supply, because we would like to see supply maintained, at least at their current levels. Late successional forest, which is in very short supply in northern Maine, comprising less than 1% of the forest area in our study area. Lynx habitat. So Canada lynx is a federally protected species that occurs in Maine, not only occurs in Maine, but Maine actually has the largest population in the lower 48. As most of you may already know, lynx prey on snowshoe hares. And we know from long-term research at the University of Maine that snowshoe hares reach their highest densities in regenerating spruce fir clear cuts, which are hard for predators to move through. And because of the decline in clear cutting that happened after Maine's Forest Practices Act, this habitat is actually starting to decline in the state. And then finally, American marten. Habitat for American marten, which is a fur bearer in the state, as well as another important mesocarnivore in our ecosystem. Marten require mature, relatively dense forest, which provides them with both the cover and the food resources that they require. So by including the late successional forest, the lynx habitat, and the marten habitat, we're capturing a wide range of sort of biodiversity conditions. So here, looking out again at the end, so circa 2070 at the end of the simulations and what has happened to these various metrics. So if there's been a reduction relative to our business as usual scenario, I've highlighted those in yellow, versus an increase in those in that particular metric. And here's where you see sort of the trade-offs. So all but an increase in plantations leads to a decline in total harvest across these examples of these different management adaptation strategies that we're showing you here. Late successional forest and marten habitat are benefited by strategies that increase the amount of mature forest on the landscape, whereas lynx habitat is benefited by strategies where there's more clear cutting. So we've got definite trade-offs here, not just in terms of the carbon outcomes, but from these different metrics. Going back to carbon for just a moment and some work that Adam has been doing with Ling Li and other collaborators. We also try to pay attention to what happens to the harvested wood, because that also matters in terms of carbon storage. So what Ling and Adam and their collaborators did was first look at trends going back to 1900 in utilization. So what was the end use for the harvested wood? Was it saw logs or pulp or biomass? They then calculated the storage in different pools associated with those end uses. Where did it end up once it was processed? And then they did sort of a small scenario analysis to consider what the impacts of new technologies would have been on those pools if they had been implemented during that time. So we've got changes in the total pools, as well as sort of the allocation, depending on what sort of technological advances that we're considering. So we're trying to pay attention to not only how much wood is coming off the landscape, as well as what's left on the landscape. We're looking at what the fate is of, in terms of carbon storage of the different product side. Trying to tie that all together in the integrated modeling. So all of this work not only includes a lot of modeling, but also working across models. Each model brings its own error and uncertainty into the mix, and that has to be carefully examined and either controlled or clearly expressed in the results. Climate change is definitely the next most influential future driver in our system after timber harvesting. And I'm finishing up work right now that incorporates climate change into the forest landscape modeling, so we can better understand what properties in our system are either resistant or resilient to increasing temperatures and precipitation, which is what's predicted for Maine. There's, of course, a lot of uncertainty in the economic data that Adam draws upon to try to understand what's happening on the market side. And there's lots of uncertainty in the marketplace. The demand for different wood products changes fast. But the industry is also always innovating to improve efficiency. So ultimately, what we have here is a very complex socioecological system with lots of moving parts that we're trying to capture enough of each one to sort of understand where the system is headed. So in summary, clearly there are trade-offs. You probably already knew that. Hopefully the work that we've shared with you here today gives you some ideas about the tools that can be used to quantify those trade-offs, as well as some potential metrics that you could use that span a wide range of outcomes. Because there are trade-offs, what we are finding, as Erin alluded to, is that the best answers probably lie in adaptation strategies that allocate area to some form of intensive management to boost carbon sequestration rates, and also to forest conservation for increased carbon storage in an otherwise working landscape that's being extensively managed. In our landscape, at least, getting landowners to harvest differently or to consider not harvesting their lands will take incentives. So this work is accumulated across a number of years and a number of grants, and in collaboration with many partners at both the federal and the state level, federal, state, and local level. We have a really interesting group here, the Cooperative Forestry Research Unit, which gives us sort of face time with Maine's landowners so that we can talk directly to them about their concerns and share our results and ensure that the sorts of strategies and methods that we're applying make sense to them as well, because oftentimes that research to knowledge translation always doesn't always happen really well, and we take that as a very serious challenge. As we are doing this complex modeling, we want to make sure that the outcomes are relevant and digestible to people other than just us. And as a part of that, I'm going to skip across that for just a moment and come back to it since I've got a little time here. So we've been, as I said, focusing on that 10 million acre area up in northern Maine, but we are expanding this to be statewide and potentially regional, moving south as we extend our work through collaborations into New Hampshire and Vermont. As we continue to get better and better at the mapping, we're also moving into forest carbon mapping as another source of information for understanding the spatial variability in forest carbon and where it's high and where it's low, and be able to putting ourselves in a position to be able to understand what's driving those sorts of differences, and are currently in the process of developing Maine's next land cover data set. So combining all of those individual species maps into a forest type map that will be made publicly available through collaboration with the state. And related to that, we've also been in active development of an interactive online web mapping tool. So back in, as I mentioned, back in the 70s when mechanized harvesting first started, was during our last outbreak of eastern spruce budworm, and the eastern spruce budworm is currently outbreaking in has been outbreaking, started quite some time ago in Quebec, has moved over into New Brunswick, and we've started to see signs in northern Maine. And to help landowners also be able to deal not only with some thinking about issues related to climate change, but also be able to think about how to minimize their risk around spruce budworm. We decided to try to figure out a better way to communicate that information through maps, while also being sensitive to the fact that not everybody has GIS experience or capacity, so experience with geographic information system, developing a really accessible web mapping tool that anybody in Maine, any landowner in Maine, could access and obtain information about risk in and around their ownership. So we've got information in here about the monitoring that's been going on. This has been a really neat effort in cooperation again with the Cooperative Forestry Research Unit, where the landowners have been putting out pheromone traps on their land so that we can keep track of changes in budworm moth populations. So we've got all that information in here. So when you click on a point, you can see the time series of data that's available there, whether that be the pheromone traps or the monitoring for larvae, which happens in the winter. So we have both of those data sets sort of there available for landowners to see. We've also used those same maps that we've been talking about to characterize forest vulnerability based off of studies that have been done looking at, well, what actually determines how vulnerable a forest is to defoliation by spruce budworm. And so we've created this one map based off of the best knowledge around forest vulnerability that we also make available. And then again, because of our interest in multi-objective management, we've taken modeling work that has been done at the University of Maine about that can be used to predict Canada lynx probability of occurrence. And again, based off of the same map, so everything's kind of one based off of the same platform, identified areas of high probability for lynx occurrence, because in many cases, what a landowner might do in order to reduce their risk for budworm, for example, might actually have impacts for Canada lynx habitat, because some of the areas where that has some of the highest snowshoe hare densities also might be some of the areas that are highest risk, at least higher risk for infestation by spruce budworm. So this is a tool that's available and out there. Its address is there at the bottom. Feel free to check it out and get in touch with us if you're interested to learn more. So with that, Erin and I would be happy to take any questions. Thanks for your attention.
All right, thanks very much to both of you. And thank you to Erin Weiskittel in the background for answering some of these questions, because we have a lot coming through and we'll likely not get to all of them. So I'll try to make sense of what has been answered and what has not yet been answered over here. So a couple of, I think a lot in the chat on methods kind of questions on different strategies to consider and so forth. And still, I might start with one that you've already answered, Erin, just because I think it might be of use to others and thinking of those watching the recording. And that is that why did you choose the Landis 2 modeling software over the Distrib modeling software or any others that the U.S. Forest Service offers for their tree atlas? Advantages of the software that you chose over others in general, for Maine in particular. What was that thought process like?
So, it was a choice that we made quite some time ago now. And it started with some early projections where we used some commercial software. We used Woodstock and Stanley to do a smaller area. And then it was like, no, we got to go bigger. We need a bigger area. We need to understand in order to understand the cumulative impacts. And at the time, we also wanted to go open source if possible. And Landis was sort of gaining attention at that point. And so we sort of took a look at it, and probably what was the single most strongest contributing factor is that there's a lot of, it has really good capabilities for modeling harvesting. And that was the driver that we were primarily interested in. And so we wanted lots of flexibility to be able to design treatments that were complex enough to capture the sort of patterns, spatial patterns we were seeing on the landscape, as well as give us lots of options for considering changes to those patterns. So it's probably in the harvesting, that's where it kind of shines.
Okay, and here we have also methods. Did you explore planting densities in the silvicultural alternatives? So a note that in Minnesota, we've seen that planting spruce too densely has negative effects on stand health and growth for saw timber products.
That's interesting. No, so density doesn't really exist in Landis 2. There are other versions which do try to get at density, and it's an active area of research by those that are developing Landis to try to increase its capacity to be able to represent density. But that in particular wasn't something we were able to look at in the current version.
So, and a handful of questions on relative density. So one, just so Maine has a high relative density. Can you talk a little bit more about that? Why is it higher than it should be? Are we seeing this primarily on working forests or on protected forests?
Sorry. Yep. I was just going to say on planting density, we do have a lot of experience with that. And we have landowners, one in particular that has a very long history of doing that at large scales. I think they've got it pretty well dialed in. And as I mentioned in my reply, we now see rotations within 30 to 35 years, which is comparable to a lot of other areas. And a lot of that's going for long-lived products. So it's a pretty, you can do it. It takes investment and it takes a long time kind of horizon that we've been trying to emphasize to landowners here. A lot of what we see here is that we may need policies that incentivize people to make those investments to do it wisely. Relative density, as I mentioned in the response, it's just a measure of the relationship between current density and the maximum biological possible density. And so that incorporates things like climate, species composition, just ecoregion, all the factors that we know affect the forest. What does we think happened in Maine, and this really surprised us, as we were expecting, we would thought Western US would be at much higher densities and not working forests like Maine or even portions of the Southeast. To me personally, I think this reflects the decline in low-grade markets that we've seen, particularly in Maine and portions of the Southeast. Right now, landowners just don't have the ability to go in and manage stands that are kind of on the margins, and so they're letting them sit longer than what they could. Problem is you kind of reach that biological threshold, and now that forest could start be releasing carbon rather than sequestering carbon. So I saw in the chat questions about PCT or commercial thinning. We advocate for those very much, but you need the markets to support it. What we think happened in the Western US is most of that forest that was above relative density has been burnt, and it's obviously below that threshold because now it's a recovering forest.
So a couple of questions on relative density and related to other components. So here, relative density and the extended rotation scenario. So your extended rotation scenario looks like it's favorable carbon results, and yet you'd think extended rotation would lead to increased relative density, and that would have negative carbon implications, is what we're hearing. So can you make sense of these sort of, are they opposing findings, or how do we make sense of that?
Yeah, I mean, an important point that's come up in the chat is really what Erin is describing as above ground carbon in the forest. So of course, if you leave the forest untouched, then the forest sequesters carbon. But I think, as we emphasize with relative density, you also put the forest in a very vulnerable position in that you make it more susceptible to future disturbances, and you also kind of increase natural mortality. And you just make that forest much more vulnerable to other disturbances like fire in the west, or even spruce budworm here in the eastern US, and all the other disturbance agents that we can talk about. I also think it depends on the state of the forest itself. I think there's this kind of naive conception that you can just let the trees continue to grow and sequester carbon, but I think that discounts the positive impacts that we've seen with management. The ability to shift towards more resilient species, the ability to kind of keep it at optimum relative densities, the ability to support long-lived forest products, and as we also emphasize, the ability to support wildlife habitat. Our concern is that if you just optimize the forest for a single objective, such as fiber or carbon, you don't recognize all of the trade-offs. And so what we would like to take is a broader ecosystem services context.
So related to that, actually, a question that I'm not sure whether you've answered it now, with these, the question about flow of products. So did the model show how the available flow of products from the forest would shift under different scenarios? So looking at the extended rotation again, what does that mean for the flow of products? And all the economic questions that come with that.
So there are multiple, maybe another strong point for Landis is that there are multiple extensions that you can sort of plug in. And the one that we use to model succession and carbon dynamics is it's been around the longest. It's sort of been vetted the most, which is why we use it. There have been, it doesn't allow you to track products, but there are newer ones that we're sort of moving into kind of shifting over to use those. So we are hoping that we will be able to do that in the future, so that the model will help take care of taking that species and age information, and as we make some assumptions about proportions that go to certain classes of products based off of the work that Adam's been doing, we can kind of more directly put those two pieces together. So not yet, but that is something that we're going to be doing in the future.
Another question on, and thank you, another question on relative density. Is this something that we should be prioritizing, that potentially carbon markets could, carbon markets or another sort of incentive structure could actually encourage people to optimize their relative density, right? So you may get carbon credits for removing trees from your forest and thus optimizing your relative density. Is it something we should be prioritizing at that level and that should be compensated?
That was the whole point of our global change biology paper. We feel like it's one of the few biologically based measures of density, and it offers the flexibility so that if you're under that kind of optimum relative density, you can do things like underplanting or PCT to bring you up into more that better spot. At the same time, if you're above that relative density, you can do certain practices like commercial thinning or other regenerative harvest that will bring that more in line. The key there is that we think it ensures a more resilient, fast growing, minimizes mortality, and just keeps the forest healthy. And what it does is it empowers the landowners who are on the ground making those decisions to do what they think is best. We see several major landowners here in Maine adapt relative density as a framework for their management actions, and they find it very supportive because you can do it both at a very high level strategic assessment in your wood supply modeling, but you can also directly translate those results into a forester that's doing a harvest. Our concern with using basal area or carbon is the only metric that most of the carbon markets are using is increasing stocking, and so you're just forcing that forest into a more vulnerable condition was our argument. Happy to put that paper in the chat, and we welcome input on that.
Yes, please do. And okay, another question here on harvest. Oh, maybe that's just been answered, whether harvest levels were kept constant. And I suppose that means over time, because obviously in a given year it wouldn't be if you're extending rotations, right?
Right. We constrained all of the scenarios that they had to be sort of plus or minus on average, well, per period within 20%, and then on average within like more 5%. So each one could kind of have a different pattern, but ultimately had to end up in about the same place. So maybe one scenario you'd see more harvest in, period 3, and then another one you might see it in period 5. So we allowed it to kind of fluctuate in that way, but otherwise constrained it pretty tightly so that the supply was as close as possible. Now we still saw those supply differences because there are certain scenarios that just can't, produce as much as others. There's just because of the management can only do so much. So that was kind of part of the analysis to try to reach the same supply level, but otherwise sort of let the scenario play out and then consider that as that's a trade-off, right? It can't quite do it. We can't achieve the same supply with that scenario, even if we sort of give it its best chance to do that.
One question on sort of running these models, and so can in particular the scenario analysis, how much can neighboring states, like looking at Vermont here and New Hampshire in particular, I suppose, right next door, how much can they expect that their results might be similar to yours in terms of the scenario analysis in particular? Is it can states piggyback on one another here, or do we expect great differences?
Well, it's interesting. So Erin's been leading, an NSF project where we have sort of interjurisdictional collaborators at the University of New Hampshire and the University of Vermont. And in both places also have landus modeling going on, where we've learned actually that there are some really interesting differences between these states in this region. And there are some common themes, but there are also some important differences in terms of like what the active footprint of harvesting is and what the general tendencies of landowners towards management strategies are all a little bit different. I think what you can take away are the big differences. So when you see these big differences between the curves, when we're looking across the entire area, their relative ranking probably is something that can kind of translate to other areas. But once you start to get down into finer levels of detail, that's probably where the commonalities start to fall apart a little bit, because then it's dependent upon the species mix, right, and how that influences productivity at the scale of a stand or, an ownership or a township or something like that. So I think broad scale, I think you can draw some similar conclusions, but you don't want to do that at finer scales.
Do you also see variation across ownership levels, or is that something you've looked at?
Yeah, so like I said, we actually, because harvesting is a sort of a strength of the landus model, we model all the owners in our study area individually. So we look at their recent patterns and just make that assumption, okay, they're going to keep harvesting in a similar way, similar rates into the future. And yes, we do can see big differences, because depending on things like harvest rate and intensity starts to impact things like turnover in species. And as one species is replaced by another, you can have big differences in productivity. Up here in northern Maine, the northern conifers are our most productive species. So as conifers, for example, get replaced by hardwoods, sometimes you're going to see a drop in productivity just because you've switched species around. And depending on harvest intensity, you can see either a little bit of that or potentially a lot of that kind of species turnover.
All right. Well, thank you very much to both of you. I will do have some more questions here, but we'll cut it there at the hour. So thank you very much. There are Erin's here, and thank you to all of the attendees who've come to listen. It's been very enjoyable and interesting to hear the presentation. So thank you.